Okay, so identifying zeros and their multiplicities. We're talking about zeros, also known as roots, solutions. What are they? They're x-intercepts. A zero has something called multiplicity. Multiplicity is the number of times that zero occurs. Okay, the number of times that zero occurs. So it says, if we graph this function that's shown right here, look at this function. How many times,
Are we writing it down?
No, we're talking.
Okay.
This is our function. F of x equals x plus 3 times x minus 2 squared times x plus 1 cubed. If I went ahead and expanded this polynomial, right? So these are linear, these are factors, right? Can you see x plus 3, x minus 2, x plus 1? Those are the factors that this polynomial is broken down into. What's the degree of this polynomial? Just by looking at it. The degree would be the highest x term once you popped them all out. 6, right? Because you would have to say, okay, this is x plus 3. This one is x minus 2 squared, so there's 2 of those. This one is x plus 1 cubed, so how many of those? Right? So if I multiplied all of these polynomials out, and I FOILed every single one of them, by the time I do that, my leading term or highest degree is going to be x to the 1, 2, 3, 4, 5, 6. X to the 6th. This is a 6th degree polynomial, right? Okay. As it is, I can see that my zeros would be at x equals what? What's my first zero that you see from this information? X equals negative 3. How many times do I have x equals 2?
2.
I have 2 of those. We say it has a multiplicity of 2 because it happens 2 times that I have x equals 2 as the zero. Look, one here and one here.
It means it bounces.
Does. How about this one? X plus 1, x plus 1, x plus 1. What's the zero? X equals negative 1. Multiplicity of 3.
That means it bounces 3 times?
It doesn't bounce 3 times. We're going to look at what that looks like in just a second. But what I need you to see here is x equals negative 3 has a multiplicity of 1 because it's only occurring in the original function up here 1 time. Can you tell? 1 time. X minus 2 occurs twice. So a multiplicity of 2. X plus 1 occurs 3 times. So that 0 has a multiplicity of 3. It doesn't change the fact that our x-intercepts are at negative 3 and 2 and negative 1. It doesn't change that. But it changes how those zeros occur on the graph. So I want to look at what they actually look like. So at x equals negative 3, that's this first zero. What was the multiplicity? 1. This is called a linear factor because it only occurs 1 time. Thus, when it crosses the x-axis, it looks almost linear. It slashes through like a line. Can you tell? The second one has even multiplicity. X minus 2 squared. So the multiplicity there is 2. Therefore, it bounces. It's going to touch the x-axis and then bounce back off. I had
Go from there to there.
Huh?
Oh, never mind.
Okay.
You got a point in my head.
Yeah, they did. And so that we're looking at the x minus 1 one, which happens 3 times. And what you can see is instead of crossing through like a line would, it really flattens out on that x-intercept. It still only touches 1 time, but it really gets flat as it approaches. If that multiplicity was odd, greater than 3, so like 5 or 7 or 9, you would see it flatten out even more along the x-axis. So as it went through, it would look almost like this. That would be multiplicity of greater than 3, but still odd. Okay. If it's multiplicity greater than 2, but still even, it's going to be pretty flat as it comes through. Okay, but it's still going to bounce. So even multiplicities bounce. Odd multiplicities go through. 1 crosses in a line. Anything else is going to flatten out as it approaches. Good? So I'm about to draw or put up here a picture that you can write in your notes. Is that better? So if you have a single 0 that occurs 1 time, it's going to cross through. That's your first example. If you have a 0 with multiplicity of 2, it's going to hit and kiss off. If you have a 0 with multiplicity of 3, it will appear flatter as it approaches and leaves the x-axis. That's what they're saying in the text. The graph will appear flatter as it approaches and leaves the x-axis. I'm going to write down underneath a definition for multiplicity because I think that that's something you need in your notes. The number of times a given factor occurs or appears. I like the word appears better. The number of times a given factor appears in the factored form of the equation. In the factored form of the equation is called the multiplicity. The number of times a given factor occurs or appears in the factored form of the equation is called the multiplicity. Do you know what factored form means? You know the difference in factored form and standard form? This is this is Standard form is going to look like f of x equals x to the 4th plus 3x cubed plus 2x squared, blah, 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 blah. That's standard form. Factored form is going to have x plus 1 times x plus 2 squared times x minus 3, whatever. That's factored form, where you can see the individual factors and you can tell what the zeros are. Do we understand the difference? So the number of times a given factor appears in the factored form of the equation is called its multiplicity. So how many times do I see x plus 1? Once. How many times do I see x plus 2? That's its multiplicity. Twice. Okay, are we clear on this concept? Okay, let's move on. I don't think this is too bad. So this is going to be example 6. Let me get my screen back to normal sized. There we go. Example 6. Example 6, it says, use the graph of the function to identify the zeros of the function and their possible multiplicities. So we're looking at this picture, and we're just picking off the zeros, and we're saying what their multiplicity might be. Oh, you got it. All right.
It's 3 and 2, right?
4, so x equals 4 with multiplicity of what?
3. This is kind of flat.
Okay, because it's kind of flat. I like it. Kind of flat. Okay, so right here, x is equal to negative 1. What you got? Multiplicity of 1. Why?
Because it just goes straight.
Because it's linear. It just cuts through.
And then
X equals negative 3. We're thinking multiplicity of 2. I go there. Not so bad, huh? That's all we're doing. We're saying, what are the multiplicities of these zeros?
It's already into it.
On this one.
No.
On this one. So if you had to write the equation for this particular function, what would that look like?
X plus 3 squared.
Okay, x plus 3, that would have you at negative 3, right? Multiplicity of 2, so squared. And what else?
X minus 4 cubed.
X minus 4 cubed. And then
X plus 1.
with nothing up there. Do we kind of see how this would work? There's one thing that we don't know based on looking at this particular graph. We don't know A. You can't eyeball it and see A. You can tell that it's positive. How do you know it's positive?
Because it's going up.
Because your tails are going up. Good. Are y'all awake?
No.
No. Well, find a way to wake up. Find a way to dig deep a little bit. Do you remember this business? This is about the tails. If the degree is even and my coefficient is positive, my tails both go up. If the degree is even and the coefficient is negative, both tails go down. And then we've got our odd positive and odd negative, right? It's going to flip-flop. So this shouldn't be news. I pulled that because I liked the diagram. I thought it looked really relevant. Okay, so if that's the case, we ought to be able to do this problem. Example 8. It says sketch the graph of a polynomial function. Sketch the graph. Bruh. So the first thing we want to do is do what? What did I have y'all walk through yesterday? Yeah, we talked about the degree first. What's the degree? 3. How do you know?
Because there's 3 x's.
There's 3 x's. You got x squared plus another one, right? So your degree here is going to be 3. What does that mean about your tails? If it's an... if down and up, right? One way or the other, they're going to be in opposite directions. How do you know for sure which way these go? What's your leading coefficient here? Negative 2.
Yeah.
A is negative 2. So now it's odd and negative. So what's about to happen? It's going to go up on the left, down on the right. Y'all seeing what I'm saying? What else can we pull? What can we find?
Zeros.
We can find our zeros. We'll do that in just a second. I want to have that conversation. Before we go there, though, I want to find the y-intercept. I want to find the y-intercept. That's going to be located at f of 0. F of 0. Meaning I'm going to plug in 0 into my function. So we've got a negative 2. We've got a 0 plus 3 squared. And we've got a 0 minus 5. F of 0 equals negative 2 times, what's 3 squared? 9 times negative 5. I would multiply the negative 2 and the negative 5. What does that make? 10, 90. So F of 0 is 90.
I ain't got enough room on one.
I know, but let's count by something bigger. Let's go like this. 30, 60, 90. See? Not scary. I don't know. It's fine. It's fine. Just count by 30s. What are my zeros?
X equals negative 3 with multiplicity of 2.
X equals negative 3 with multiplicity of 2.
Oh, 5.
And x equals 5. See? So at negative 3, what's it going to do?
Bounce.
It's going to bounce. At x equals 5, it's going to go through.
Down.
We know that our tail goes up on the far left. It's going to bounce off of that x. It's going to go up through the y-intercept. And then it better come back down. I don't know where it comes back down. Again, that would be in calculus that we would go figure that out. But this is the general shape. Why don't you get on that back there? Figure out where the 0 is. Cool? This is your function. Not the 0. I don't want to know about the 0. I want to know about the vertex. I don't know where that extreme is. I know there's one right here, but I know there has to be another turning point somewhere so that it comes back through that x-intercept. He'll let us know in a little bit. Don't know where that happens. Stay tuned. Okay, here comes example 10. This is the last example. This is example 10. It says, okay, you should be able to write the formula given the graph. Bruh.
Both positive.
Okay, so both tails go up, so your degree is even. Even degree, is that what you meant by both positive? Okay, what's happening? You're lost?
No, I'm good. I'm great.
How can I help you?
Never better. I'm good.
Do I need to go back a slide?
Nah.
No, he was wondering if we were writing anything.
Not yet. We're looking at this picture. You want to draw this picture?
No.
Draw it. Then we will write the formula. I'll give you time. Draw it. Draw it beautifully. Make note of where it crosses the x-axis and the y-axis and the other x-axis over yonder. Oh, we had another one. Good call. It's beautiful. Draw it. Wyatt's is going to have shading and be three-dimensional and all kinds of goodness. Did you draw it?
Oh, yeah.
Okay. Excellent. Where are your x-intercepts, Britton?
-3,
Okay. X equals -3. What else?
2,
X equals 2 and
5.
x equals 5. Okay. Talk to me about the multiplicity at -3. How many times do you think that factor occurs?
1.
Only once. So this one has multiplicity of 1. And how about at 2?
2.
Maybe 2? Multiplicity of 2. And at 5?
1.
Maybe 1 again. Now, does that make sense? With an even degree, if I count out my multiplicities, what would my degree end up being? 4. Does it work? Yeah, we said I need to have an even degree. If I count up my multiplicities, I've got 1, 2, 3, 4. That's even, right?
Oh, yeah.
So we're good. So it seems to be making sense so far. Okay. When I write out these factors, I like to start this in factored form. Okay. It's best to put these pieces of information, our x-intercepts, into our function in factored form. So this is going to look like x plus 3. Remember, we reverse the sign when we're writing the linear factor. When we're saying what is the x-intercept, we keep the sign as it appears on the graph. We've got x minus 2. How do I show multiplicity of 2? Squared. Good. And we've got x minus 5. We've got 2 ways of figuring out what a is. We know a is positive. We know there's some kind of coefficient that could be any number but 1, right? It could be 1. We don't know what a is. We know it's positive because why? Because both tails are going up. We've got to be able to solve for it, okay? To solve for that a value, we need a point off the graph. You can pick any point off the graph. I would say if your y-intercept is an option, that's your best point. Okay? In that y-intercept, there is an x and a y piece of information. Are you following what I'm saying? In the y-intercept, you get an x value and a y value. What's the point for this particular y-intercept? 0, -2. So what we know is when x is 0, y is -2. So watch. We can solve for a by plugging in the information from this point. When x is 0, so I'm going to have 0 plus 3, 0 minus 2, 0 minus 5. I'm going to keep a. That's the piece of information I don't know. And we're going to set it equal to what? When x is 0, y is -2. This is how we're using our y-intercept. And we're solving for that a value. Are you following what we're putting down right now? Okay. So we've got -2 is equal to a, whatever that a number is, we're solving for it, we don't know it. A times what comes out of the first factor when x is 0? 0 plus 3 is 3. -2 squared, 4. 0 minus 5, and these are all 3 multiplied together. It's 12 times -5. -60. So you got -2 equals a times -60. How can we solve for a?
Get rid of 60.
Get how?
You add it.
It's negative and we're multiplying.
Divide.
Divide. Good call. I saw what you were saying right there. Divide by it on both sides. And so now I've got -2 over -60. That reduces down to be 1/30. 1 over 30. That's your A. So you got to solve for it. You're going to take your zeros and another point and use that information to solve for A, and now we can write our function. And so our function, when everything is put together in factored form, f of x equals, what's that A value?
130.
Which works. It needed to be positive because my tails have to go up. 1/30 times x plus 3 times x minus 2 squared times, somebody graph it. Check us out. Make sure we're right. You're graphing it?
You said someone.
Someone.
Yeah, she got it.
We got Abby.
And her. And her.
Look at them.
I thought she was
Yamala doesn't need to graph it. She knows we didn't make a mistake. She didn't make a mistake back there. It's good? Does it match the picture? Isn't that cool?
Wow.
This cool relative? You want to try it? Did you?
Yeah, 151.704.
So this extreme is at 151.7, comma, I'm thinking probably 2-ish.
7/3.
7/3. 6/3 would be 2. So 7/3. Good. Yeah. Nice job. Thank you. 151. I told y'all he would find it in a little bit. Anyways, all right, so let's do the last one. This is one more. It's exactly like the example we just did.
You said the last example was left.
Well, do you want to try it, or do you want to just go for it on your homework without another example?
Go for it.
You think you're good?
Yeah.
Oh, yeah.
Maisie, you get to pick. Do we do another example? No peer pressure. We don't need another one?
I don't think so.
Okay. Okay, well, the majority of your homework is going to be from this right here. Being able to pick up your zeros, plug in any point for x and y, and use that information to solve for A. You got it?
Yeah.
Okay. Bet.